Hello there, welcome to another problem from JEE this year 2025. So this from paper 1 and this question number 3. This turns out to be really simple question. Just have to not panic and then you should be able to answer this question. So here is a square loop and magnetic field is, I've read this, so I know magnetic field is only in this this y greater than 0 area. That's what the magnetic field is. It's pointed towards the z-axis, so it's like b0 k hat. All right, but actually this is a time dependent, and so the time dependence is cosine omega t. That means, and then it also says this was what it was at t equal to 0. So t equal to 0 start rotating at time t equal to 0 loop, it starts rotating about the x-axis, about this axis, in a clockwise fashion, as viewed from the positive x-axis. So initially is in the xyz plane. So this is a t equal to 0. So it was t equal to 0, it was like this. So there was no magnetic field going through the loop. As it rotates, more and more magnetic field will go. When it comes all the way here, after quarter cycle, t equals to quarter cycle. So what is the cycle period? If you look at this, cycle period will be 2 pi over omega. So quarter cycle will be pi over 2 omega. Half cycle will be pi over omega. And when it goes to the half cycle, I didn't really draw right. This goes like this at t equals. At half cycle, it will be exactly in the opposite direction. So this is t equals to half cycle. And if you look at even go further, so from here to back to here is t equals to half cycle to full cycle. So over here there's no b0. Okay, so that's how it's going to rotate. And the question is, which one of this corresponds to the induced EMF? The V here, V is for V at t is induced EMF. So if you remember Faraday's law, then you should be able to answer this question. The problem is V can be plus, minus, plus or minus, plus or minus, plus or minus, right? So what's the minus, what's the plus in the induced EMF? So this would be the Faraday law minus the magnetic flux through the loop. This is the magnetic flux through the loop. This stuff, flux through the loop, and the rate at which it changes with a negative sign. So if this is increasing, so because we just have to worry about here not actual magnitude, So it's going to be plus if phi b increasing through the loop, increasing, negative if decreasing. And it turns out to be sufficient to actually solve this problem, and 0 if not changing. So clearly, if you can look at it, at t equal to 0 to t equals to, at this fast is increasing. That means I should get negative. So here is the here this is quarter cycle. This is quarter cycle. This is half cycle. This is 3/4 cycle, and this is the this is the full cycle. This is the full cycle, and then kind of repeats like that. So this is one whole cycle. That's one thing. So you could see right here it's increasing. So here expect V negative, and initially it was nothing to something, right? So the rate would be very high here, and increasingly it will be more steady. So it won't be 0. V is not 0 at t equal to 0, and V less than 0. So V not 0 at t equal to 0, V not 0 at t equal to 0, V. So between this and this, we have to decide, right? So both of them okay so far. So this okay, but we got to choose between the two, which one is more okay. Now, after half cycle out here is all 0. So V equal to 0 after t equals to half to t equals to t. So this is okay. This is the half cycle. This full cycle, and this is not okay. This should be 0. So this is already answer. So the answer is A. Okay. Another way to do it. This you saw me go through the argument, but you can another argument says, okay. So I know that t less than t between t over 2 and t, this should be 0. So we'll say, oh, this guy and this guy, both are okay. Now I'm going to decide between this and this. Well, how do we decide between this and this? Again, you have to go back to the 0. And what do you expect at the 0 time? At the 0 time, you expect non-zero value. Why do you expect non-zero value? So you can do a little bit math if you wanted. So at 0 time, you're going to have to do limit so it's going to be how much area does it see? It sees only this area, and so this will be the projected area. So projected area would be whatever area it is times sine theta times b, which is going to be b0 cosine omega t. Sine theta is omega t, so it's going to be minus d by dt. Let's call it a b0 over 2, and this is going to be sine 2 omega t. So you do it out, it's going to be minus ab0 over 2 times 2 cosine omega t, omega 2t. These two cancels that, and it's going to be, and at t equal to 0, it's just going to be minus a b0. That's all. That's going to be. So that's going to be EMF at t equal to 0. So which is not 0. The area is the area of the loop, and this is the projected area. And theta is this theta. As the theta increases, you can see as the 90 degrees, when theta is 90 degrees, you have the maximum area through which the magnetic field is going. So this is some algebra you can do to get here, but you can see I did not need to do any of this algebra. I just need to make sure that I follow this sign that's in front of d phi by dt, and that another thing I needed to follow was at t equal to 0, it better not be 0, because it's going from a little bit less than t is 0, no magnetic field, but a little greater than t, there's a magnetic field. So the derivative will not be 0. So that's what I had to do. Okay, this was a pretty simple problem. There's another question that actually does Faraday law. That's question number 5. I'm going to do that after do a question number 4, and check that out also in just maybe another hour or so. I'm going to post that one too. Bye.